Good afternoon, everyone. My name is Paul Johnson. I'm a client IT specialist in the New York metropolitan area, and it is my privilege to introduce this session, Session 21070, ZVM vSwitch, Advanced Topics vSwitch Part 2. Please silence your phones. Please remember to complete the survey. And Alan has asked that we ask questions right throughout the session. It is my privilege to introduce Alan, who helps me consistently through the course of any given year. Alan?
Thank you, Paul. Good afternoon. Welcome back. Now the fun begins. All right. Like we weren't having fun before. I know we were. So let's talk. What are we going to talk about? So we're going to talk about some of the more advanced use cases for the virtual switch. We're going to talk about link aggregation, commonly also known as channel bonding. I'm going to talk about link aggregation groups shared across multiple LPARs. All right, we're going to talk about the hypersocket bridge, what VEPA is, a little bit about monitoring with SNMP if we have time, but I also want to spend a few minutes with you on diagnostics, things that will help you figure out why isn't it working and what did I do to get into this situation. Okay? So first of all, link aggregation. Well, the first thing on this chart to note is that link aggregation has been promoted by the IEEE. It's no longer 802.3AD, it's now 802.1AX. Ooh, and the letters have been capitalized, which means it's a full standard. It's no longer an add-on to another standard. So it has its own place in the world now. All right, in link aggregation, what we try to do, well, I guess it's important to first look at what we've done traditionally from an HA perspective. So in HA, what we do is we use an OSA port, and if it dies for any reason, we switch to another OSA port. Now what that means is at any given instant in time, I have access to the bandwidth of a single port. Okay, I can only do 10 gig per second. Okay, that's the best I can come up with. Now, from link aggregation says what I want to do is take multiple cables, multiple ports, wrap them together, and send data down them concurrently. Instead of serially, I'm now able to send data in parallel. All right, so there we go from serial back to parallel, then we did SCON, now we're at FICON. Anyway, so things move along, so now we're back to parallel interfaces, and I can have 2 all the way up to 8 OSAs together. So I could, in a theoretical sense, get to an aggregate bandwidth of 80 gig per second, okay, because I can do them all at once. And in this case, I really am operating them all at once. One of the things that drove some interest in link aggregation was people buying OSAs and then sitting there unused. Well, IT managers going, I paid for it, I want it to be used. Well, if we were using it, it wouldn't be backup, would it? Okay. The purpose is that it's not used. But this way you actually do, backups are great. Your backup access to you try to use it and then discover it's not plugged in either. Right, so at least with link aggregation, we actually also find out everything, we find out the status of everything all at once. If there's a problem, we let you know. But in this case, what this chart is really trying to show you is that link aggregation takes virtual NICs. So forget about guests. I'm not interested in the guests. I'm interested in all the virtual NICs that all the guests are using, right? Some guests have 2, they may have 3, 4, whatever, and many guests only have 1. It really doesn't matter. Just take all those NICs and put them together and then start dropping the traffic on one of the physical OSA ports. Okay, the virtual switch's job in this case is to decide what virtual MAC address, what virtual NIC, done it on a MAC address basis. But what will be the association of virtual NIC to OSA port? So the virtual switch is managing that, and it moves the association around in an attempt to load balance. Okay? Now there's, work is in progress to continually improve the load balancing. Okay? But every few minutes, the virtual switch will double check to see whether or not it has what its virtual NIC to port assignment looks like. So that ratio, it wants to be sure that ratio is even. Right now, it doesn't really care how much traffic a particular virtual NIC is using. And some of these improvements look at, I need to take traffic, rate, frames per second, into consideration. Because I might want to pile up several NICs that are being used lightly onto one port and maybe only put a few NICs that are being used more heavily on another. It's up to virtual switch to decide that. So that's why this technology will continue to evolve and try to make better choices. Now, what's happening now this is a piece of intelligence, and it's on the other side of this connection. So the virtual switch is on one side, and it's plugged into all of these ports. On the other side is another piece of intelligence. The switch has a management endpoint in it, which is actually communicating with the virtual switch. Okay, so the virtual switch is in communication on its own. It's talking to an agent, if you will, running inside the physical switch. They are communicating about the status of this link. Okay, there are various terms for this thing. Cisco calls this a port channel. Okay, and it just means it's, they say, oh, it's a port channel. They give the port channel a number. It consists of so many specific ports are bound into it. Okay, but the port channel is being managed by an endpoint in the physical switch. Now, the other thing I'm showing you here is that in a best practice configuration, so physical switches are appliances, and they get maintained, they get rebooted, they fail, okay? They get restarted, just because. And I don't want, because of a switch goes down, there's a reason I've got multiple OSes for high availability. If they're all plugged into the same switch, how does that help me? I've just now got another single point of failure. Okay, so there's technology that exists on, I believe, all the major vendors of switches do this. It's known by a variety of names. Virtual chassis, or VC, is probably the most common name for it. And what it does is it lets me take two physical switches. They're trunked together. There's a trunk between them. And they themselves are sharing the idea of what is going on. They're sharing state with regards to the status of this. So what it means is that if I were to lose one of these switches, the link aggregation group remains up, and these other two OSes can still run. Okay? Now, VM has no idea that this is taking place. It's not supposed to know. It's designed so you don't have to know. Right? And so if it loses one of these, VM will be perfectly happy with that. In the normal case, these things are communicating. I have a command I can issue that I'll show you that says, remove port 1 from the link aggregation group, from the port group. So remove that from the port group, and it communicates with the other side and says, I'm going to remove port 1 from the port group. Are you okay? Let me know when that's okay. He said, okay, I've taken all the traffic I had that was going to come in on that port, and I've requeued it somewhere else. You're good to go. And then VM can now take that port out of the group and says, I've taken it out of the group. Then the physical switch says, okay, I've taken it out of the group, we're good. And if I want to add one in, he says, I'm going to add one into the group. Okay, I've got him. So there's this link aggregation control protocol. So LACP is the communication that's taking place between switches. This function is done with physical switches as well. So link aggregation really started out as a way to say, back when we had slow links, right? You had 10 megabit links. You'd take several of them together. Okay, so link aggregation is not a new technology. Okay? But then it really was for bandwidth. Now I'm less interested in bandwidth. I'm more interested in the high availability that comes with it. So if data is trying to move through one of these and there's a failure, okay, any data that we haven't actually sent will actually get requeued onto one of the other OSes. Any data that was in flight when this went down, as far as VM is concerned, the data is lost. Okay, and he just keeps going. What'll happen eventually for TCP, TCP will discover I didn't receive some data and ask it to be retransmitted. So the applications will, or the IP stacks up here will be notified and they will retransmit data. Okay? That's how TCP works. That's exactly what the TCP part of TCP/IP is for and how it has reliable data delivery. Okay? But the virtual switch itself will just throw that away. There are capabilities in the protocol that over time we may look at, which allows us to say, have the switch recognize how much data it lost, back up, and then retransmit that data again over one of the other links. So that's within the power of the protocol. VM does not implement that capability. Okay. So we call this the aggregator or the multiplexer. So you can see this when you're trying to read literature. A lot of nomenclature pops up, which can go what. So when I talk about, to me, it's just the agent, the management agent inside the switch, and the various vendors use various names for that. Okay, so that is link aggregation. So up to 8 OSes. Best practice spread over 2 switches, such that I am then protected from loss of an OSA port, bad cable, bad adapter in a switch, loss of switch. Even better, of course, because I have 2 power, in the best case, if I'm lucky, I've got 2 power sources into the raised floor, right? Switch A is plugged into one side, switch B is plugged into the other. Okay? So I try to look for all my single points of failure and try to get rid of them. Sometimes you can't get rid, it just is what it is. Okay? But at least that's easy and reasonable. Did you do everything reasonable to help prevent the problem? So what, it cost you a few $1,000s and you didn't do it? Oh, okay. Again, one of these things only supported on Ethernet mode vSwitches. So again, why I had you skip, don't bother with doing IP vSwitches. And to show you how hard this is, you issue a command set port group, you give it a name, and you tell it what OSes you want. Now this syntax, you see this f200.p1, that's port 1. The default is port 0. For those OSes that have multiple ports on the chipid, you can specify which one. Okay? So this effectively creates a port group called channel 1 and puts those 2 ports in it. When I define the vSwitch, instead of saying rdev and giving it the specific OSes I wanted to use, I instead specify the group name. I'm done. Okay? That's all it takes to do it. Okay? Now, there's a rule about this. Now that link aggregation control protocol means I can have only one cook in the kitchen. All right? I can't share this OSA with somebody else who's not playing my game. Okay? So other LPARs cannot use this, except in a case I'll show you. There's a very specific case you can share it, but you're not going to share it with ZOS. You're not going to share it with a Linux LPAR. You're not going to share it with a Linux virtual machine. You're not going, this is something that's running link aggregation control protocol, and anything that's not doing that can't use it. All right? So we do have something called shared port groups, very specific. ZVM63, ZVM64, and you need a Z13 or a Z14. Okay? It takes hardware. It takes OSA changes to make it happen. And what this means is that, for example, a 4-member SSI cluster will use at least 8 ports, typically. Why? Because I'm going to have 2 ports per member. All right? Now, I got 4 members in a cluster, so a total of 8 ports. If I have 4 clusters, I'm up to 32. The zeros are starting to appear at the end of on the bill, right? And people are now starting to ask me questions. I will point out we have a limit of 48 OSD channel paths on the system. So if I'm at 10 gig, those are single port cards. So therefore, if these are all 10 gigs, I have 8 more before I got to buy another machine. I'm okay with that. If you need to buy another machine, I have operators standing by to take your order now. Okay. So you can end up just looking at the network hardware. This is some of the things when people look at that TCO number and they talk about, wow, look at all the networking hardware that people have to purchase in the more distributed or less consolidated environments. All right. So what we would like to be able to do, what people had asked that we be able to do, is to be able to, in fact, share these ports among the LPARs. Okay? And I can do that with what the lab calls shared lag, shared link aggregation groups. All right, to make that happen, first of all, it has to be vSwitches. Again, I cannot sharing with anything else. It's a vSwitch sharing. So that means it's ZVM only and only for vSwitches. You can't take, oh, I'm going to take this OSA, share it with that LPAR. It's going to use, it's going to be assigned to the vSwitch over here, but over here I'm going to use it for VM TCP IP. No, vSwitches only. Okay. So I need two things to make this happen. I need a way for the LPARs to talk to each other, to communicate with each other, so that the vSwitches, the vSwitch instances can talk to each other. And we have an inter-vSwitch link or an IVL. So in some cases, data will flow over that connection in some very bizarre error scenarios. But in general, it's providing only management information is going back and forth. The second thing I need, now that I can communicate, now that the instances of CP can talk to each other, I can now create an actual global vSwitch. Create a vSwitch and define it in a way that says I'm spanning this vSwitch across all these LPARs. All these LPARs are in communication with each other, and so we can coordinate what's happening. And oh, by the way, the point here is about sharing OSAs. So I hate to say it, it should hopefully be obvious. We're talking about within a single KEC, right? Because we're sharing OSAs. This has nothing to do with your other KEC, right? So this is just what I'm doing in a single machine. So a global vSwitch does not span KECs. It's only for the local. So first of all, IBM went out, ZVM development went out to the IEEE and registered a new multicast group with them. So multicast group is a specific MAC address which is defined in a way that says people will join, they will start listening. If they listen to that particular, start picking up frames for that particular MAC address, then they're hearing the buzz, the background buzz between the systems that are participating in that protocol. That's how dynamic routers work. You know, dynamic routing, they all are listening to each other on a special multicast group. So what happens, so first of all, now that the vSwitches are listening, you can, it's really CP, the CP instance that's listening and passing the messages along. But if you want to think about it, think of each vSwitch you create is actually listening to the conversation out there. Okay? And if I make a vSwitch configuration change on one member, that change is automatically propagated to the others. Okay? I don't have to go to each member, each one that's sharing it, and go and make the same configuration change. So you can manage the port group, that shared port group. So remember the port group, the thing we defined that had the multiple OSAs in it. So that port group is now being shared across all the members, or whatever, however many I like. All right. And I can choose just whatever system I happen to be logged onto at the moment. I can change the attributes of the port group, and it changes everywhere. I've said that one LPAR handles LACP. That's sort of only half true. They can all do it, but only one will do it at any given instant. Now, so we had those two constructs, the IVL and the global vSwitch. So the IVL, the inter-vSwitch link, we have what we call IVL domains. And a domain is a collection of global vSwitches. And I can have multiple domains, each with its set of global vSwitches. Maybe these systems are in this domain, this is in that domain, some are in both. Oh no, wait. We're going to find out I can only be in one domain. So some LPARs choose what domain they're going to be in. All right. There are some very specific error conditions. Think about an OSA that's being shared among multiple LPARs. The idea that the OSA could only go offline to one LPAR, that kind of makes no sense. If you unplug it, it's unplugged from all LPARs, right? But there are some internal things in the machine which can cause it to go to disconnect from just a single LPAR. And in that case, that is when it might start being used to transmit data. Okay, you might see data flowing through the domain. But that's a theoretical thing. I haven't actually seen that happen, but architecturally it could. Because I said, why is this? And the developers point me to some internal architecture. See right here, it says right here that can go offline to a single LPAR. Well, how does that happen? We don't know, but it says in the book. Okay, all right. Does it have to be that complicated? It says right here in the book. Okay, so all VM hypervisors in the same, trying to share that port group, have to be in the same domain. And we create that domain through the vSwitch. And we define a vSwitch, we give it a name, but we say it's type IVL. That type, there's those type Ethernet ones we've been doing. So we're going to create a special one of type IVL. And I'm going to say what VLAN I want it, or what domain is it. The domains are A through H. And you can have at most 8 of these in a KEK. Okay? And if you will be communicating, so these IVL, so it's a vSwitch, it will have OSAs attached to it. It's a vSwitch. It's communicating over the network. It will have uplinks. Okay? Now, that uplink could be a conventional RDEV or it could be an exclusive port group. Remember, this is for managing shared port groups. I'm trying to set up the thing to manage shared port groups. I can't use a shared port group to do that. Okay? Otherwise, VM's head would explode. All right? So you can use an exclusive port group from that. And because I might be using conventional RDEVs, they could be just plain old shared OSAs if I wanted. Old school shared OSAs. But maybe we're in different VLAN IDs on that network, in which case I can specify the VLAN ID. From my perspective, when you plug VM into a network device, it needs to be in a trunk port, because it's just going to come in handy eventually. Okay? And switching it later is just a pain. All right? Easy, but you have to fill out paperwork and stuff. All right, so my VM system will indicate what domain is it a member of. And everybody else who's going to be having the port groups that I'm sharing with, we all will define a vSwitch. We don't care what its name is, but you can guess it's probably going to be the same everywhere. All right, and we will all specify the same domain name. So I could have all these domains even in the same VLAN. But this is how we logically segregate the information. So, traffic is running around in this LAN segment for multiple domains. It's fine. Okay? It's not going to hurt anything because all that data is tagged with the domain. But you can do a VLAN if you want to segregate that traffic. There's no requirement, but you can. In this picture, what I've got is I've created the IVL vSwitch and this old school sharing. That's just typical shared OSAs as I've been able to do for decades. Right? And because I still want if one of the interfaces in the IVL goes down, I need redundancy. I need something to back it up. So I've got these 2 LPARs. Casey and Jones are the names of the ZVM systems running in there. And they both create a vSwitch. They both called it IVL. All right? And they're pointing to different, this one over here says its primary is 7200 port 0. Its backup is 8200 port 1. Over here, its uplink, its primary is, again, 7200 port 0, 8200 port 1. So they're using the same backup, the same ports for backup and primary. Now, what I want to, I can actually change things, because now on set vSwitch, you can set vSwitch, give the name, and say IVL port, in which case I want to change the IVL related attributes. I can change that VLAN ID if I want. Oh, did it wrong, need to change it. You don't have to take the vSwitch down to do that. You can just change its VLAN ID. You can, reset, start all over. What I can tell, so since I was a developer for almost 30 years, I know development stuff when I see it. And this is obviously for development. That was for their benefit. Oh, I need to reset it because it's not working right. Until I get all my code correct, then I don't need this option anymore, but it's still there, okay? Because you never know. And then there's a set vSwitch IVL port ping. So you can actually check to see what your connectivity is to verify, one ping only, Vasily, that you can get to the other hypervisors. Okay? And there actually is a heartbeat out there that he checks to see that everybody else is there. Okay? Because if he's not there, then I have to one of the other LPARs has to take over his duties with regards to housekeeping. Right? So the difficult part about setting this up is that you have to add the shared keyword. Okay. Now what's kind of cool, now remember really ports are really chipids, right? P-chids, and device numbers are for weenies. Okay. Device numbers, it doesn't really matter. That's an arbitrary human thing we like because we don't want to keep track of subchannel IDs. Right? When the XAIO showed up, everything changed. I still need device numbers because I like them, okay? Not because I need them. Well, what's kind of cool is that if once this port group is now shared and active among the multiple LPARs, I don't really care what the device numbers are. The different LPARs could be accessing the same chipid with different device numbers. I don't care. In the LPAR in which I issue this command, I'll specify the devices as they're known in my LPAR. The other CPs will figure it out. If it's a different device number, it doesn't matter. So it's not going to go to the other system and try. If I said join 700, it's not going to go to the other systems and join 700. It's going to look on my system, say, what chipid is that? More importantly, what P-chip is it? And tell the other systems, you need to get a device on port 0 on this P-chip. And then it'll figure out what chipid do I need, therefore let me find an available device number on it, okay? And it'll figure it out. You don't have to worry about that. And those devices become effectively attached to system so that you can't use them for other things, right? And so anything that you change, so if you want to add, delete, remove things from the port group, just go ahead. And you can be logged on to the other systems, doesn't matter. So that's being communicated around all LPARs. If you don't believe it, then there's a query command for people who don't have faith. Okay. So you can query the port groups, you can query you query them by group name. There's even this way to say, that group that we created, the port group, there's an instance of that port group for each system that's a member of the domain. Okay? If I wanted to, I can query group name.instance, and the instance is the system ID. So I can query VSW1.system A while I'm on system B, okay, because they're all there. Okay, so at this point, I've got the infrastructure, the IVL is now set up, okay? And I've created a port group on the IVL. Okay, now that I have a port group, a shared port group, I can now create a global vSwitch because the global vSwitch needs a shared port group to work. Again, very difficult. We now add the global keyword. Okay, everything else is the same. And this says, when I put that keyword on there, it says that this group needs to be a shared group. It will get upset if it isn't. Okay, if you try to use what we call, if it's not shared, it's called an exclusive port group. Okay, if you try to put an exclusive port group there, you're going to get an error because you can't have a global vSwitch unless the port group is shared around all the LPARs. All right, now this vSwitch name will be the same because it's a global vSwitch, so I'm going to define it with the same name everywhere. And there will be, the system will actually create an instance of that. System ID.name gets generated. And we can see these things in various queries. You'll see them. You don't rarely have to use them unless you're talking to the support center and they ask you to issue some special command. But generally, you're not going to worry about these system-specific instances. You can have multiple global vSwitches per LPAR. You can have the two vSwitches, which might be part of the global, part of the port group, could be on the same LPAR. I can now share OSes, link aggregation groups, even if I just want to do this within an LPAR. I can actually set them up and we can share the OSes between two vSwitches. Before I had to have it to use link aggregation, I had to have my own port group. Now I can have multiple vSwitches share that port group. So here's a set example of a set port group named lag. It's LACP, it's active, these are the defaults, and it's shared. I will put devices 6100 and 6200. Both will default to port 0. Okay? And I will define a vSwitch called network with the global attribute, and I will reference the lag group. So what happens is that through the IVL, this all gets communicated, and there will be first of all, the shared port group lag. There'll be the one in the LPAR Casey. Okay? It will be created with 6100 and 6200, and the same group will be created over in LPAR Jones. Okay? And because I'm intelligent, it actually are the same addresses in the multiple LPARs. People who create different addresses for the same devices in different LPARs are taken out back and shot. Okay. There's no coming back from that. I've seen them be different when someone's trying to take a CAC I'm kind of trying to bring that in and keep everything. That LPAR looks like my old machine, which wasn't configured like this one, and I want to keep the device addresses. And it's like, you're just delaying the inevitable, dude. You're going to have to go through that system and renumber those devices. You can't keep it up forever. So that gets created. The shared port group gets created, and then when I define the global vSwitch, multiple instances get created. The vSwitch, Casey.network, okay, and Jones.network. And, for convenience, I'm talking about the dot thing. So when you create vSwitches up to now, you've always had to say system. Guess what appears in that spot now? That's where these names come from. So all of a sudden, you'll know that you are seeing an instance of a global vSwitch because it doesn't say system anymore. It now has your system's node name in there, your system ID. Okay? And this just says what I said. All right, so link aggregation, you all got that, right? Big pipe, we're doing parallel stuff. I can take things in and out easily out of the port group. It's de rigueur for switch-to-switch communication. The core, everything is done with link aggregation. More and more sites are moving to link aggregation just because it's simpler. Just for one thing, we just do it. Okay? And other platforms, Linux talks about channel bonding. Okay? You can go look, Linux does 13 different kinds of channel bonding or something. One of them is this. I mean, there are ways to, this is sort of a formal, true sharing because the other side knows I'm sharing. Okay? Other forms of channel bonding are a little bit, he doesn't really know, I'm just taking advantage of the ignorance of the network. Okay? All right? So you're going to want to use a pair of switches that support that virtual chassis function we talked about, right? Again, so you will be able to have a cross physical switch. So you're protecting yourself from switch outage. You will use 2 OSA ports on different PCHIDs. So that if it is a multi-port card, if I lose one of the ports, I'm probably gonna lose the other one. Okay, something has gone seriously wrong. So you're trying to get to a point, if you're gonna bother doing this, it's like, what is my objective? What are the things I can protect myself from? And what haven't I protected? Was it worth my effort to bother? So a single source power failure, which took out one of my switches, took out half the power out of the machine, out of the Z14, right? Somebody reboots my switch, which more or less is a power failure as far as I'm concerned, right? I've got switch port failures, OSA port failures, a firmware upgrade takes your OSA offline. I'm doing a firmware, applying a firmware patch, and it says it's concurrent, but it really goes offline briefly, or I need to do a config off-on to make it happen. Okay? It makes it a lot easier to handle these sorts of things. All right, that's link aggregation. And that's probably what people are most active with the vSwitch are doing the most with today. Okay, most questions I get, okay, how are we going to do link aggregation? I'm like, the same way you've been doing link aggregation everywhere else, in your enterprise. It's new to you, it's not new to your network teams. All right, the hypersocket virtual bridge, virtual switch bridge. Now, this is kind of a cool capability for those who like to exploit hypersockets. And we like hypersockets. For those who aren't CPU bound, who aren't running near the end, hypersockets can give you a significant performance boost, right? And what I'm showing here so I've got two CACs here. And what I have on the left side, I've got 3 LPARs, and these red boxes here are all Linux guests, okay? And what I've got, these are ZVM LPARs. And in LPAR 1, 2, and 3, and 4, I have created what's called a vSwitch hypersocket bridge. So I've created a special kind of vSwitch, and its job, remember our job bridge, takes traffic from one interface and moves it to another. We talked about that in the last hour. So I create this, and what it's bridging is a local hypersocket. It's bridging a hypersocket chipid out onto the network and back. Now, what's kind of cool about this, I have multiple VMLPARs that are sharing that hypersocket chipid. That's how the guests are getting into it. Excuse me. If for any reason LPAR 1 goes down, the firmware will choose one of these other 2 LPARs. It will choose which one, and it will activate, because these are in standby. These virtual switches down here in the shaded area, those are there, but they're in standby mode. They will wake up in the event the hardware says, you're it. Okay? So it's up to the hypersocket, and actually it's the hypersocket chipid which is making the choice. You can prefer one and say, this is my primary one, and that'll be your primary. Okay? You can choose that if it goes down, and it's been switched over here, do you want it to go back? When LPAR 1 comes back up, do you want it to go back? Or do you want it to just stay wherever it left it? And this goes a lot to, how did I provision this virtual switch? Does it have link ag? Okay, is the same capacity in LPAR 2 down here? Oops, I only got 1 OSA here. I only got 1 OSA here because I thought I would never use these. But once you're over on them, now what kind of HA do you have? Nothing. Okay, so that goes down, then this whole vSwitch has to move again. I'm kind of out of luck, actually. If I lose this connection to the OSA, it's just a normal vSwitch. Guess what? Only traffic, it'll just be able to deal with traffic up here. It won't be able to proxy it, won't be able to bridge it out to the network. But per hypersocket chiplet, and remember you have 32 of these things. Okay? Each one of those can have a bridge, an optional bridge to the outside world. Okay? Every Linux guest connected to that same hypersocket chiplet will be on there. So, what's kind of cool is I've got this Linux guest in LPAR 2 talking to a Linux guest in LPAR 3, my WebSphere talking to my Oracle. Okay? And somebody does live guest relocation of this guest out of LPAR 2 over into LPAR 4. Now, before the hypersocket bridge, I had to have two interfaces in that virtual machine. I had to have an Ethernet connection, and I had to have a hypersocket. Because we're communicating on the hypersocket, now I'm in another CAC. Hypersockets don't span CACs. What am I going to do? How am I going to talk to him? Oh, I got dynamic routing. I can figure out all. Oh, I got to go through this my Ethernet interface now. Now I don't have to worry about that. Okay, they're communicating with each other in here in the same CAC. The virtual machine gets moved. They're still talking to each other using the same MAC addresses and everything. They think they're on the same hypersocket. They ask the device, "You're a hypersocket, right?" It is. It's a physical hypersocket. But the data is being, because the destination MAC address is gone, it's no longer on this hypersocket, then it's automatically being handed by the hypersocket firmware is handing the frame to the vSwitch. The vSwitch is then putting it out here onto the physical network. It's being picked up over here. Well, why is it being picked up over there? Because the MAC address got registered in the OSA. So the hypersocket NICs have MAC addresses. Okay? Good news, they have burned in MAC addresses. So I don't have to worry about managing those. And he will all of a sudden appear over here and we can still talk. Now, does anybody remember something very significant about the difference of a hypersocket network from an Ethernet network? The MTU size. Okay? With a hypersocket, I can use like 64K MTU sizes. Very efficient. Excellent for streaming data. Very fast. But out here, this might be only 1500 or 8K if they're jumbo frames, right? So in that case, I need a way to tell the Linux guest, you need to make your MTU size smaller. Good news, the vSwitch takes care of that. Okay? Anytime it finds out that it's proxying, it's saying, you're trying to send data and I have to send it out, he will automatically generate a path MTU discovery packet and send it back to the guest. Because the guest is probably trying to send a 64K packet, a 64K frame, and the vSwitch is going, I'm going to discard this. Okay, because it won't fit out here. Because I know what the MTU size is here because you told me. Okay, and it's not going to fit. So I'm going to throw the packet away, generate an MTU discovery, and you will automatically resend that. You'll fragment it and resend it. It will now be small enough to fit out here. All right? Linux, being the good doobie that it is, polls every so often to see what the MTU size, how big can it let me see if I can make that bigger, see if that works now. Okay? So it was using large MTU sizes. I moved it, now it's automatically switched to using smaller MTU sizes. I'm done doing whatever I had to do. I took LPAR 2 down. I brought it back up. Now I'm relocating that virtual machine back over to LPAR 2. Linux will eventually discover, I can use a larger MTU size because I'm no longer going through this. When I relocated him back over here, he just started communicating. He was using 1500 MTU size, and then, and then in a few minutes, however long that takes, whatever cycle Linux is on, he'll discover, oh, I can get back to 64K again, and then he's back fast. So that's a very nice feature of the bridge. Now, I have to say, So what everybody wants to do is connect it to ZOS. You can't connect ZOS on this. If you want ZOS to connect to this thing, you need to have ZOS. You need to submit requirements to ZOS, to COM server, okay? Because they don't support the mechanisms, the hardware mechanisms it takes to do this. So it's not a VM issue, it's a ZOS issue, okay? It's not even a HyperSockets issue, it's a ZOS issue. All right. So this LAN segment up here, just like in a real vSwitch, this HyperSocket becomes an extension of this LAN segment. Okay? I can tell the vSwitch that this HyperSocket is VLAN 57 out here. Okay? So it knows what to do, how to get the data, what the right settings are to proxy that data out into the Ethernet. Okay? I can have up to 5 of those bridges. Okay? So 5 bridges, and you can have, and I believe that's up to 5 bridges. No, it's 5 bridges per HyperSocket per CAC. I can't remember. Okay. And as I said, that HyperSocket bridge can be fully configured with its uplink can be a shared, port group. Everything that the vSwitch can do is available to the HyperSocket bridge as well. And so the real issue here being forgetting about ZOS, the point is that I can now just have a HyperSocket connection if I want. So I can go, look, you guys can talk. The Linux guests are allowed to talk to each other on the same LAN segment. Okay, they're not going through a firewall. On the same LAN segment, they can take advantage of the HyperSocket. Okay, and if I relocate the guest to another CAC, it continues to work. Okay, the guest doesn't have to change its networking because I moved it to a different CAC. All right, very difficult. Define the vSwitch with the usual suspects, but I'm adding this Bridgeport keyword, and I'm pointing to a particular RDEV that's on the HyperSocket. I don't need more than one here because HyperSockets, you can't unplug them, right? You don't trip over their cables. I mean, you can yank the chipids out from the LPARs, but then you get what you deserve, okay? But generally, you'd specify a device on there that's really pointing to a chipid, is all it really is. And you indicate whether this is going to be the primary. You do have to change how you define the HyperSocket. Okay, wherever you had said X0, now you say X4, whatever you would have put there before, because that first one got you the maximum frame size. Okay. HTD fully supports this, so it's not you don't have to do it in the IOCP. All right, so questions about the HyperSocket bridge? Okay. Because we love standards, there's a really cool standard called the Virtual Ethernet Port Aggregator. I've also seen Virtual Edge Port Aggregator. But the 802.1q standard, which we talked about, was the Metropolitan Networks. That's the trunking standard, right? Well, there's a modification to that standard. So what Q says, here's the rule. When I try to figure out what's failing on a network, it really helps if you understand how it's supposed to work. So you recognize when you're seeing failing behavior, non-conformant behavior. The rule in a switch says, if the switch is looking out through all of its ports, it's watching for traffic's coming in, and a switch receives something on one of its ports, it has one major rule. Whatever you do, do not send that packet, that frame, back out to the port that you just received it from. It prevents broadcast storms. Okay? Because you send it back, and he says, well, I'll send it back, I'll send it back, I'll send it back, and everybody does nothing, but it's a hall of mirrors. I don't know, when the photon dies, then it'll stop reflecting. Okay? So we don't like that because we've been there, done that. The early days of Ethernet were full of broadcast storms. It's a nice way to bring down a network as well. So rules went into place. And we call that the hairpin turn. Okay? You can't send it back. Perfect rule unless you're doing virtualization. Because what I would like to do, the idea is that, you know, switches have a lot of cool capability. For one thing, intrusion detection modules. They need to see traffic. So what do I do if I got two virtual machines that want to talk to each other, but I've got intrusion detection running out there in the switch? Well, normally I would just deliver it guest to guest. The switch didn't see it, so it can't judge it, okay? And under normal rules, if I sent it, I can't get it back. He won't send it back to me, okay? It looks like it's just been filtered out, which of course it has. But I'd like him to say, no, if it's, I will check. I will check the origin MAC address. I will check the destination MAC address. And if I think that's okay, I'll allow it. Or if I say, well, that's okay, let me look at the traffic in more detail. Oh, and I think that's okay. He's allowed to send it back, okay? But you have to tell a switch that you understand, you promise, you will not create a broadcast storm when it does stuff like this, okay? That you know what you're doing, all right? And so switches, physical switches, have a capability to negotiate with the other endpoint over whether or not they, one, will support VEPA, they'll support the hairpin turn, and whether or not, well, basically whether they support it and whether or not we'll use it, okay? And this is all done down, you know, when Ethernet, when you're plugging things in, it's not just an electrical connection. Yes, but how fast are we going to send data? You know, you plug a 10 gig port into a 1 gig port, how do you know how fast it's going to go? The 10 gig port has to know not to send more than 1 gig, right? It physically can, it's just a cable with fiber optics in it, right? The cable doesn't care. So speed negotiation happens when you plug things in. You just never see it, it's just magic. And we worry about full duplex, half duplex, and speed negotiation. VEPA is part of that, low layer, where I can find out whether the other end supports it. So if you do a query vSwitch, you will see whether or not that switch supports VEPA. If it does, you can issue the set vSwitch VEPA on. Now when I do that, every single frame that a guest sends will go out the wire, every single time. No exceptions. It will not short circuit inside the OSA. It will not short circuit anywhere. It's going all the way out the wire. If I get it back, great. If I don't, I wasn't intended to get it. The destination is prohibited from seeing that frame. Okay? But CP will only go into that mode if he sees that the virtual, you can't override and say, well, do VEPA anyway, because he knows whether the switch will support it or not. Okay, so you can't force it. All right, so VEPA implies isolation. I have a set vSwitch isolate on command, which says, forget the VEPA thing. I just want all my traffic going out there because none of my guests ever talk to each other. It's not for that. For example, I have all my virtual machines, each is connected to various user networks, but they all are connected to my single management network because they're all streaming their backups out to the same network, okay? But they're not supposed to talk to each other over that backup network. In fact, in the physical world, Cisco has a term they call a private VLAN, which lets you put all the ports on that VLAN, but it prohibits cross-port communication on that particular LAN segment. They might be able to do it on other VLANs, but not on that one. Perfect for backups, because I don't have to worry about cross-talk, back channels, all that, and I'm not going to worry about it. Okay, so that's how you can set isolate onto a virtual switch. Unfortunately, it's at a virtual switch level. And both of these are at a virtual switch level, not at a VLAN level. I wanted to get isolation modified so that it would work on a VLAN level, but the hardware doesn't support that idea. Okay, so you don't have to do any hardware configuration at all. You don't have to turn it on or anything. It's either the hardware supports it or it doesn't. All right, So questions on VEPA? Remember, VEPA is great when you want to offload all of the filtering, all of the monitoring, everything. And and people say, oh my God, you really want all the packets going off and on? Yes, because that's where my intrusion detection software is. And the last thing I want to do is get yelled at because I'm bypassing the security software. Well, we thought all your virtual machines would go through that. Well, it shows how much you know about what I'm doing. Okay? So people just kind of assume. So perhaps this is how you fulfill their assumption. Okay. SNMP. Switches can be monitored. There's a standard that describes how to monitor a switch with SNMP. SNMP, Simple Network Management Protocol. It's not overly simple. Okay, it's not just for networks. Okay, and management, it's more like a monitoring thing typically. I can monitor a vSwitch. You can do something like, you can have netcool, omnibus, netcool, monitoring switches and tell you what their status is, what all the port states are. Because, that port went down, not good. I mean, we manage our switches, our important devices, they get managed like hosts, okay? Because the host went down. Yes, that's because the host is up, but I can't tell because the port went down. Something failed in the switch, okay? I need to know that, right? So our virtual switch can be monitored. Every virtual switch can be effectively given an IP address that represents the virtual switch. And if a status changes on virtual ports or the uplinks, it will report through SNMP that I've generated a trap saying this port went up, port went down. I mean, I haven't really heard of anybody doing this, only because when you reboot a virtual switch, you've rebooted your whole system, typically. I mean, it's just part of that.
What about like load and throughput on the switches?
So load and throughput on the virtual switches, what about those? I haven't seen, first of all, I haven't seen any issues regarding people having to worry about throughput on the virtual switch because you would add another OSA to it if you needed that, and VM's own performance data is telling you that information. Also, a lot of good performance data comes from the switches themselves. In fact, I'd say you're going to get better data out of the switch, because the switch will tell you how it's utilizing each of the ports. And by the way, so that load balancing I was talking about, the switch does that also. Both sides will balance. So sometimes VM will do what it's doing in its simplistic way, and the switches are much more sophisticated. Yeah, I got this, and it rebalances it in a way that's better. Okay. So you could use this to monitor, but you're not going to get a ton of information. We can tell you how many packets. We can tell you, and you can do the math. Say I queried it, a minute later, and it was this many more packets. So how many packets per minute per second is doing. So it's really kind of simplistic. And again, I haven't heard of anybody saying, gotta have it. But it's there if you need it. Okay, so somebody, oh no, we can't use virtual switches. Well, what else are you going to use? Okay, because they can't do that. Now, finally, just a couple of minutes on diagnostics. Some commands that you need to know. Okay, query VMLAN, query vSwitch active, and query NIC details. Query vSwitch active, I can find out what users, what virtual machines are connected to it. I can find out what IP addresses are active on that virtual switch. Because I told you in the last hour that CP watches the ARP responses, and he knows what NICs are being owned, what IP addresses are being claimed by particular virtual machines. Okay? It can also be interesting if you say, that's not the IP address I assigned to that guest. What's it doing with that one? Okay, so you can actually run some checks if you want it. Query NIC details, where I can actually find out, I can tell by the status I see in there whether you even brought your adapter up. Did the virtual machine correctly initialize the adapter, or I gave it a virtual NIC, wrong address. So it didn't even try to initialize it. Okay? I can find out how many bytes and packets have been sent or received. Okay? And so I give you a table here. For example, I want to look at the discard counters. They're the things that help me a lot. If I see a received discard count inbound, it's telling me about inbound packets. And what it means, if I issue on query vSwitch active, so I ask the vSwitch, tell me about your receive discard count. What it means is there's a definition mismatch in the vSwitch. I have received a packet that has a VLAN ID I'm not using. Okay? There's no guest with that VLAN, is using that VLAN ID, authorized for that VLAN ID who's up and has an active NIC. Therefore, I just discard the packet. Okay? It also means I may have coded VLAN unaware on a trunk. I'm getting VLAN tags, but I'm configured to not expect them. So every single packet is being thrown on the floor because they're not valid. Okay? But I can also look at it from the NIC, the guest's perspective. If I see receiving packets being discarded, it's because they're arriving faster than I can process them. Two virtual machines trying to talk to each other, and if there's a lot of network traffic between them, they need to have approximately the same share values. Because if one can send tons and the other guy can only receive a little, eventually we're going to overrun him. Okay? I went to send you more, but you haven't received everything out of your buffers yet. What's the problem? Well, you're not giving him enough CPU time. Okay? So you can tell you about that. Transmission, I've overrun the physical OSes, for example. I haven't actually seen that. But the point is that, you know, as the machine gets faster, you have to also increase the bandwidth of the network. Otherwise, I could just send more packets than you can process. Okay? That's going to become more and more of a problem. So you might have to say, I need to go to 10 gigs. I've got 1 gigs. I need to go to 10s. And then being able to see these other problems. So you can reset counters if you want to look. So you've looked at them. You've decided I do or don't have a problem. Whatever. You can set vSwitch counters clear, and they'll reset to 0. Okay? So it just helps with the diagnostic. That's what I have for you in these last 2 hours talking about vSwitches. I hope it's been helpful. This particular purpose of this chart, again, is to just tell you that there's a lot of stuff in virtual switches, and there will be more stuff in virtual switches over time. Continues to be a virtual networking is a very important area of investment for the ZVM team. If you have questions about vSwitches or you need me to come into your site and help you figure all this stuff out, happy to do that. Does anybody have any questions for me? Yep.
A question on vSwitches. We have clients come in with ZOS guests, and they run VIPA. What kind of support do we see in vSwitches with VIPA?
vSwitches are VIPA agnostic. We don't care whether the guests use VIPA or not. It is I happen to be one of these proponents who says I don't need VIPA, but that's for a variety of other reasons. I know ZOS needs it, but none of the rest of it. Linux doesn't need VIPA, ZVM doesn't need VIPA, because we're providing our failover at layer 2, rather than we don't need failover at layer 3. But yeah, ZOS is going to have its VIPAs, and I would say that when they are guests using virtual switches, they probably don't need them for same subnet VIPA. 2 adapters into the same subnet, I got a vSwitch. I'm already handling that. They won't need those 2 adapters. Okay? But it's more trouble to have an alternate configuration than is just leave it. Yep. Okay? All right. Thank you very much. Please fill out the session evaluation forms. Appreciate it.